Hi, and welcome to aUniversity. I'm Piotr Urbanski, Associate Director of Marketing Science here at Ayzenberg. Today we're going to talk about, well, it depends. I'll walk through conditional effects in regression analysis, also commonly called interactions or interactive effects. After this short course, you'll know how to come up with conditional hypotheses and how to test them. You'll also learn how to handle and present these in context of regression analysis. I'll also point you in the right direction to learn about more advanced types of conditional hypotheses, as well as where to find code to implement them and visualize them. I'll also point you in the right direction to learn about more advanced types of conditional hypotheses, as well as where to find code how to implement them and visualize them. This course is great for analysts and data scientists trying to put statistical confidence in statements where it depends. This course is also great for anyone trying to better understand results of conditional analysis and to ask the right questions. Let's review some concepts. First, let's quickly recap the traditional scientific hypothesis. At the fundamental level, a hypothesis is an explicit and clear statement of how two observed phenomena are related. There are a lot of different ways to phrase these, depending on the context. And in the causal inference setting, there is always some implication that something is causing something else. For example, a deterministic statement might be that if it rains, then things will get wet. We rarely work with these types of statements, as there is not much to test here. A hypothesis could be directional. If the amount of rain increases, the number of car accidents increases. While most likely true, there are still things to test because it'll depend on a number of factors such as tire technology. Similarly, hypotheses can also be probabilistic. If we observe earthquakes, then earthquakes are more likely. What about conditional hypotheses? We still use the same logic and framework, but there's an additional factor to consider. Your prediction will vary depending on something else. For example, we might have some factor that conditions our relationship between two phenomena. For example, if everyone uses snow tires, then when it snows a lot, there might be less accidents. But if no one uses snow tires, then when it snows a lot, there might be more accidents. Let's dive in. There are a lot of different types of conditional hypotheses. I'll quickly go through some examples and go into a more detailed example. One example might be where there is no effect at low values of our conditional variable and a positive effect at high values. Another one, no effect at low values and negative at high, positive at low values and none at high, or negative at low values and none at high, or maybe even no effect at all. Or how about this one? No conditional effect, but it's positive across all values of your conditional variable. Another one is when it switches, negative effect at low values and positive at high values. And finally, positive effect at low values and negative at high values. So let's dive into some applications. Conditional effects need to be plotted to be best conveyed to your audience. Though you could take a few reference points and show them in the table. However, I would recommend against that, as even slight changes can be pretty meaningful. Let's quickly review a simple linear regression. The equation of a line is given as y equals a plus bx, where y is our outcome variable, here it's conversions, and this should always be plotted on the y-axis. A is the y-intercept. This is where the line intersects the y-axis. And b, or beta coefficient, is the rate of change or slope of the line. This is how much y changes per 1 unit change of x. And x, this is our input variable. This should be plotted on the x-axis. Careful in the plotting, in some contexts there's an implied causal relationship where x causes y. So always plot your x on the x-axis and y on your y-axis. In a regression with two groups, we can split this into two categories with two different intercepts by introducing a dummy variable. I recommend watching our video on Simpson's paradox for another way to think about these. Here b is still the same. It's the change in y per 1 unit change in x. This simple model assumes it's the same rate for both groups. So in our data, we create a new variable called d for a dummy variable. This is just a column in our data set that takes a value of 0 for group A, our baseline group, and a value of 1 for b, our comparison group. Our model will now estimate us a second beta. This is going to be the difference in the intercept between group A and group B. Our previous model only gave us different intercepts. We can extend this even further to yield different slopes. To do so, we add one additional term to our regression equation. Our initial beta now should not be interpreted out of context. we have now to consider d. When d is 0, then the beta is still the change in y per 1 unit change in x. And for beta 2, it's still a difference in slopes. But now we have the beta 3. This is going to be the difference in the rate of change between our groups. It's the incremental increase or decrease from the original beta when d equals 1. Let's take it even further. We have reviewed how to do conditional analysis when you have two groups. You can always extend that methodology to multiple groups. However, what do you do when you have a continuous variable that conditions your effect? That is a variable that could take on a wide range of values that doesn't neatly fit into groups or categories. We saw these plots earlier. This looks like a regression plot, but it's not. On your x-axis, you still have some variable from your data. We're going to call it z for now to distinguish it from everything else. But on the y-axis, you have the marginal effect. This is no longer the y or output variable. Another way to think about this is that these are values of your beta coefficient at different points of your z. It's a tiny bit more complicated than that, but not by much. We'll get into the calculation of marginal effects in a second. In this example, we have the marginal effect as positive in the low values of z. Notice that it's also plotting the confidence intervals. In this case, the confidence intervals do not overlap our 0 line, which means that the estimated effect is statistically significant. The middle part does overlap 0, as we transition from low values of z to high. That means the model is telling us there is no statistically significant effect in this area. However, if you wanted to fine-tune this and see if there's some form of curved or step effect, you could. And at high values of z, we see that the model is telling us that there is statistically significant negative effect. So here is an example of where we have effects that are in opposite directions depending on how big the value of z is. When it's small, the effect of x is positive, and when z is big, the effect of x is negative. This is really just an extension of our earlier model we reviewed. Instead of that dummy variable interacting with x, we now have a second continuous variable z. Again, we can't just interpret the betas in isolation. We have to calculate the marginal effect. So our marginal effect of x, that is how x influences y, is calculated as beta 1 plus beta 3 times the value of z you're interested in. So you decide, in this case, what the value of z is, and you calculate the plot. You'll want to stick to reasonable values that are informed by your data. Often you'll see people plot the frequency of the z data points to be transparent on if you do or don't have enough data to be confident at these different points of z. To get some great code and read some great papers on this subject, I recommend checking out Professor Matt Golder's website. It's simply mattgolder.com. Navigate to his section on interactions and read carefully. He's got code for doing the analysis and plots, some example data sets for each, and papers on how best to think about this type of analysis. You can easily extend this to as many variables as you want. Just be warned, it becomes increasingly difficult to do so and keep track of everything as you're trying to plot all 3 interactions or more. Here we have a 3-way interaction with 3 continuous variables. One really important thing to note here is that we must include all components in these interactions. We have x, z, and w in the model by themselves. We have the interaction of x times z, x times w, and w times z. We also have x times z times w, and of course our intercept. On our x-axis, we've stuck with plotting the values of z. On our y-axis, we're still going to have the marginal effect, but now we're plotting multiple lines for different values of w. Now w has taken values of 1, 2, and 3, and 4, but this could easily be anything and everything in between. It's our job as analysts to choose the values that are meaningful to display and to communicate. Adding w does complicate our calculation of the marginal effect a bit, but not by much. I recommend keeping careful notes on what you're doing and where you're plotting what. The marginal effect of x on y is now dependent on z and w. In this case of this extended equation, it's equal to beta 1 plus beta 4 times the chosen value of z plus beta 5 times the chosen value of w plus beta 7 times the chosen value of z and the same value of w. You'll then need to repeat this for all the various different values of w you want to plot. In this example, there are also these little dots that denote where there is statistical significance, because having 4 sets of confidence intervals introduces 8 more lines and it would be difficult to read. But you could easily plot these in different colors that might help distinguish these confidence intervals, or maybe even do a 3D plot. And a few parting thoughts. Where do you have conditional effects in your analysis? Where do you expect the cause to have an effect sometimes but not other times? Where do you expect the cause to change the direction of its effect? Thank you for joining us for aUniversity.